In this video, I will show you the fundamental connection between the geometry of states and entropy. If you studied thermodynamics, you already have a sense that volumes in physical space are connected to entropy. Both volume and entropy are extensive quantities. So if you take two equal volumes of the same gas, you have double the size, but you also have double the entropy. So you can use the volume to measure the entropy, but you can also use the entropy to measure the volume. Something similar, but much deeper, happens for state spaces. The state space of both classical and quantum mechanics come equipped with a geometric structure, which is what allows you to define Hamiltonians, Lagrangian, and define the equations of motion. Now, that same geometrical structure allows you to calculate the entropy for classical and quantum ensembles in statistical mechanics. Nothing new so far. The kicker is that you can go back. If I don't give you the geometric structure, but I gave you the entropy for all ensembles, you can recover the geometric structure. Therefore, the geometric structure and the entropic structure are the same thing. Geometry is entropy, and entropy is geometry. At an intuitive level, the geometry of states defines sizes in terms of a number of states, a number of configurations. Entropy quantifies the variability of states of configuration within an ensemble. That is, an ensemble is the set of all possible preparation coming from the same preparation procedure. The entropy tells you how much variability is there among those preparations, how different they are from each other. Therefore, it makes sense that being able to quantify the variability among states and quantifying the number of states themselves, well, they're the same thing. You can do one, you can do the other. This connection tells you that the general perspective that statistical mechanics is built on top of mechanics is actually wrong. In fact, you can start doing statistical mechanics and recover the standard mechanics in the limit case where the ensembles are more and more precise. Basically, standard mechanics and statistical mechanics are the same thing. You cannot define one without implicitly defining the other. But this is all words, and as I always say in this channel, you should not take my word for it, you should see the details. So, let's look at the details like we always do. First, let's review the geometry of classical mechanics and its connection to the entropy. Mathematically, the geometry of classical mechanics is given by what is called the symplectic form, which is a fancy name for something that essentially quantifies the areas, the number of configuration for a degree of freedom. So if we have a single degree of freedom, the symplectic form is giving us the area of this infinitesimal parallelogram, and so it's essentially dq times dp. The infinitesimal difference in position with the infinitesimal difference in momentum. If you have a region U instead, if we have a bigger region U, then you can calculate the number of states, the number of configuration in U, simply by taking the integral of the symplectic form within that area. So this is going to be the integral of U of dq dp. So it's going to give you that area. So the symplectic form essentially is defining areas in phase space, and these areas in phase space are the count of configuration. And Q and P are conjugate quantity really because the product of the differences in position and momentum give you count number of states. And that's why when you're doing statistical mechanics, it's important that you're using momentum and not velocity, because velocity and position are not conjugate quantity. Okay, so with this, now we can go and calculate the entropy, which is what I call the Gibbs-Shannon entropy, not to be confused with the Boltzmann entropy, the log of this measure. This can be defined for any probability distribution. And any probability distribution, the value of the density at a point is defined essentially not really at the point, but on this infinitesimal area. And the infinitesimal area times the density gives you this infinitesimal parallelepiped, which has the amount of probability that it's in this region. If we want to calculate the entropy, then we simply do minus rho log rho of dq dp. And this is just omega, right? So when we're calculating the entropy, we are actually already using the definition of the symplectic form, the count of states, and there is no way to do it without it. You need to have this geometrical information to be able to calculate this entropy, because again, the entropy has to be the variability of the states of the configuration, and so you need to know how you count the configuration, and this density, this probability density, has to be in terms of position and momentum on the configuration and not other variables. Okay, so this is essentially how it works, and if you studied statistical mechanics, this shouldn't be news to you. So conceptually what we have, we start with the geometric structure, which is given mathematically by this symplectic form. From this geometric structure we can create a measure that counts the configuration by doing the integral of the symplectic form, and you can get the entropy by doing this minus integral of rho log rho times the infinitesimal area, and so from the geometric structure we can calculate all these things. And now the question is, can we go the other way? So here we started with the geometry, we led to the entropy. Can we take the entropy and then go back to the geometry? So how does that work? Well, so let's look at uniform distribution over a region of U. So we have position and momentum, we have a region U here, and this would be the uniform distribution that it's on that region. The value when we are in the region is 1 over the size of the region, so the total area, and the probability distribution outside of the region is equal to 0. And we can confirm that this integrates to 1, because if we make the integral of the probability distribution on the whole space, well, this is equal to doing the integral over just the region U, because it's 0 everywhere else, of 1 over the count of states in U. And so what we have here, so since this is a constant, it goes outside, and we just have the integral of the QdP. But the integral of the QdP is really the count of states. So we just have mu of u over mu of u, you get 1. So this is actually a probability that is normalized. It's a uniform distribution over the states defined in the region U. Now, let's go and calculate the entropy for this distribution. And so we just apply the numbers, apply the definition. We have minus the integral of rho u log rho u in the QdP. Again, outside of the region, this is going to be 0, so we just integrate over u, and we substitute 1 over mu u in both places. Now this, the logarithm of mu u with the minus becomes the inverse, so like minus the logarithm is the logarithm of the inverse, so this is just the logarithm of mu, and since mu is a constant, we can take this outside, and we can also bring this outside, and so we just have this constant with the integral of u of the QdP. But this integral of the QdP is just mu of u. Mu of u simplifies with mu of u, and so you just have logarithm of mu of u, right? So this is the logarithm of the count on configuration, which again we're recovering Boltzmann entropy, sometimes called the Boltzmann entropy, the idea that the entropy is the logarithm of the count on configuration, and this is only true if you have a uniform distribution. If you have a distribution that is not uniform, then you need to go and use the Gibbs channel entropy. Okay, so the entropy of the uniform distribution recovers the count of configuration, and you can see that this is an invertible function. We can go from one to the other. There is, though, a little bit of a detail that we have to specify here, that uniformity is not coordinate invariant. So if we have something that is uniform over the variable x, and we have another distribution here that it's not uniform with the variable x, and if we make a change of coordinates, we go from x to the third, well, this that was uniform becomes not uniform anymore, and something that is uniform in the new coordinate was actually not uniform in the original coordinate. So this is something where you have to be a little bit careful of, because if I just gave you these space of distribution and you don't really know exactly which one is uniform, which one is not, how can you go and recover the space of those uniform distribution where you can make that convenient transformation between the entropy and the logarithm of the count of configuration. Well, what you have is that uniform distribution are actually those that maximize the entropy within a region. So if we take the set of all the distribution that are zero outside, right? If you take the set of all those distribution, then you can pick the one, you can find the one that is uniform just by knowing the entropy of all the distribution, because you go find the one that has the highest entropy, and that one is the uniform distribution. So not only you can go and say, okay, if I have the entropy of all uniform distributions, I can go back and find the measure, the count of state for that region. Well, you can also find the uniform distribution from all the other distributions. So you can recover really what are the canonical variables, the position and momentum, because you find these distributions that are uniform. So here in mathematically, we take the set of all the distributions that are zero outside the region of U. We take all the entropy of all those distributions. We take the biggest one. We take the exponential of that supremum, and then we know that that's going to be the measure of the measure of the count of states within that region. Then you can shrink that measure to an infinitesimal size and recover the symplectic form, recover the count of configuration for an infinitesimal area. So this is how it works. We go from the entropy, we again find this supremum, we find the entropies, the distribution that are uniform, that are the ones that are the highest entropy, so we recover the measure of the count of configuration for all the subsets of the space, and from this we can go and recover the areas of infinitesimal surfaces, which is the symplectic form. So yes, we can go the other way. If you give me the geometry, we can calculate the entropy, but if you give me all the entropies, I can go and recover the geometry. So to sum up, we have three structures. We have the geometric structure, and then we have the measure theoretic structure, the one that counts the configuration and gives us the probability for our distribution. And then we have this entropic structure, the one that we go and use in thermodynamics and information theory and statistical mechanics. And the key here is that if we have use uniform distributions, we can go and connect these three structures one to the other. So the geometry of phase space is purely entropic in the sense that it's exactly the structure that we need to be able to calculate the entropy and therefore to do statistical mechanics. Okay, so this was for classical mechanics, and you say, okay, how is going to work for quantum mechanics? Well, for quantum mechanics, it's kind of the same but different. The geometry in quantum mechanics is given by the inner product. It's essentially given by the Born rule. So for example, if we have a spin 1/2 or a qubit, we have a direction in space, what happens is that this would be the geometry of all the possible states that you have, one for each direction of space. And the inner product is going to tell you, is going to be dependent on the angle between two states. So this two arrows represent the psi and the phi, 2 points on the surface that represents two pure states. And the probability, the inner product, right, from going from one to the other, inner product between the two, is given by the cosine square of the angle divided by 2, right? There is this divided by 2 because in quantum mechanics, two different possible value of a measurement are orthogonal to each other. So spin up and spin down are orthogonal in quantum mechanics, even though the angle between, the vertical direction between up and down is 180 degrees. And so this is why you have this divided by 2. So if you take the inner product between spin up and spin up, of course, this is going to be 1. The probability is you're going to get the same thing, and therefore this is the cosine of 0, and it is 1. If they're orthogonal, if they're opposite of each other, then they're orthogonal in phase space, and you expect this inner product to be 0, and in fact you would have 180 degrees divided by 2, it's cosine of 90, which is 0, cosine square is 0, so perfect. And if you take instead the vertical direction and some horizontal direction, this would be a 90-degree angle in physical space, and in the Hilbert space it becomes a 45-degree angle, and so you have the cosine square of 45 degrees, which is 1/2, which is exactly what you would have here. So there is this link between the geometry, which is given by the inner product, the probability, because it's the probability given by the Born rule, and how is this connected to the entropy? How can we make a connection between the geometry and the entropy? Well, that's not very hard. We just look at the entropy of the mixed state of two elements where we have an equal mixture. So we can take a mixed state, which is 50% psi plus 50% phi, and we can show that the entropy of this mixed state depends uniquely from the inner product. And so, again, you shouldn't take my word for it, so let's prove it. Now, the proof here is very geometrical, and again, I understand that most people that study quantum mechanics are not taught the geometry of quantum mechanics, so I'll try to go more slowly. I also have other videos on the geometry of quantum mechanics, and if you want more videos on the geometry of quantum mechanics, leave a comment below. But this, essentially, this circle, you can think it as a section of the block ball, right? And that's what it is. So you have the center here is going to be the maximally mixed state, the one where you have the 50% of the spin up and spin down, or spin left or spin right, and so on. And the circle represents the pure state. So when we are taking phi and psi here, there are 2 points on the surface. Now the space of mixture is a convex set, meaning that you find the mixtures exactly in the line that connects the two. So if this is psi and this is phi, and our rho is an equal mixture of the two, well, rho is going to be in the middle point of the line that connects the two. This is our rho. And now what we want to do is express rho in terms of or an orthogonal basis, because if we express rho in terms of orthogonal basis, we are diagonalizing the density matrix, and therefore we are finding the eigenstates and the eigenvalue. So what does this mean that we are going to diagonalize the matrix geometrically? Well, in this case, rho is here, and this is the center. So if we take a line that connects rho to the center and we extend it, right, then we find the 2 points A and B, and these are they are on the circumference, so they are pure states, and they are opposite to each other, therefore they are orthogonal. So A and B are orthogonal states, and since rho is on the line that connects them, rho is a mixture of A and B. So rho is a mixture of A and B, which are orthogonal, and so A and B diagonalizes rho, which is exactly what we want. And now we essentially want to be able to find the eigenstates, the eigenvalues of A and B, so that we can find what are the two probabilities that we're mixing A and B to get rho. And again, these are linear combinations, so the way that it works is that the component of B, how much probability we have to give to B, is going to be the length from A to rho divided the length from A to B, right? So it's the ratio of this side with respect to the whole line. And again, this is where it becomes a little bit counterintuitive, because you would think that since we're finding the coefficient from B, you would want this side of the line, and no, it works the other way. And you can think about it that if we had the B, right, B would be a mixture of 100% B and 0 A, right? So if we are here, the coefficient that we have to put on B is 1, so it's the whole line. And as we go farther away here, we are going to get less and less of B. So it kind of works in the opposite that you would expect geometrically, but actually conceptually it's correct. Okay, so we can say that rho is equal the distance between A and rho divided the distance from A and B times B, so this is the probability of having B, and the distance between rho and B divided by the distance between A and B, that gives us the probability of having A. So we can write rho in terms of this linear combination. So this is the diagonalization of rho. Okay, so now it becomes a geometrical problem of calculating these distances. A and B, it's easy. If we imagine that the radius is 1, A and B is the diameter, so it's going to be worth 2, and so we put 2 and 2 here. The distance between A and rho can be thought as the distance between A and C plus the distance of C and rho, and the distance of A and C is the radius, so it's 1. And the distance between B and rho is the distance between B and C, which is again radius that is 1, minus the distance between C and rho. So we get to this expression. So now we just have to find what is the distance between C and rho. Well, you can see this is a right triangle, right? Since it's a right triangle, this is just the cosine of this angle. So C rho is the cosine of the angle between psi and B. But the angle between psi and B is half the angle of the angle between psi and phi. So we can write that the distance here is the cosine of the angle between psi and B, which is equal to the cosine of half the angle between psi and phi. But the cosine of half the angle between psi and phi is the norm of the inner product. So rho is actually 1 plus the inner product divided by 2 times B plus 1 minus the norm of the inner product divided by 2 times A. So these are the probability coefficient that we have to put in front of A and B to get our mixture of states. And now we have this. Now it's going to be super easy to go and calculate the entropy. How do we do it? Well, we just use the Shannon entropy. This is going to be the entropy of these two coefficients. So it's minus the first coefficient logarithm of the first coefficient minus the second coefficient times the logarithm of the second coefficient. So again, we saw that from the geometry, from the inner product, we can go and calculate the entropy of the mixture of any pair of states. And again, the question is going to be, can we go the other way? Can we, given the entropy, go and reconstruct the norm of the inner product? So let's look at the function that from the inner product gives us the entropy, right? This very, very ugly function. We can plot it, and the plot is just this. The function goes from 0, 1 to 1, 0 monotonically. It always decreases, so this function is invertible. If I told you the entropy of the mixture of two elements, you would be able to recover the inner product by inverting this function. So yes, we can go the other way. If you give me all the states and not the inner product, but we give me the entropy of an equal mixture of the two states, then you can recover the inner product, you can recover the whole geometry. Again, so we have these three structures. We have the geometry, which is given by the inner product. We have the probability that is given, again, by the square of the inner product. And you have the entropy that, again, you can go calculating by using the inner product. And so, again, if you give me one of these three things, I can go and calculate the other. So, again, this means that the geometry of quantum states is purely entropic. It's exactly the structure that you need to be able to calculate the entropy. So this is the overall message. The geometry of classical and quantum states is purely entropic. It's exactly the structure you need to recover the entropy. There are other results that I'm not going to be covered here that again are results from our reverse physics approach, we can go and show that the invariance of the entropy across observer is what gives us this pairs of variable, position and momentum. That's a structure where you can define an entropy that is invariant under coordinate transformation and changes of unit and so on. And another thing that you should know is that the quantum space state, that ball that we saw and the projective Hilbert spaces are symplectic exactly because they are complex. So the fact that we have complex Hilbert spaces is essentially because we have the symplectic structure, which is this idea of pairs of variables. If you didn't have one, you didn't have the other. So there are even more links that one can make between the entropy and the geometric structure. Then we are not going to look at them today. Again, what I really want to get across in this video is that statistical mechanics is part of the structure of the state spaces. So when you define classical mechanics and quantum mechanics, the space themselves are designed so that you can do statistical mechanics. That structure is not something that you just sprinkle on top of the state space, is already there in the state space. So this idea that often there is in the foundation of physics that statistical mechanics is a sort of a second-class citizen, the pure states are the things that are important. No. The pure states are essentially already statistical elements because the geometry of pure states is there to give us the entropy and the structure that we need for statistical mechanics. So now may you ask, but Gabriel, you only talked about the geometry of phase space, the geometry of states. What about the geometry of space-time? Well, one of the things that is interesting is that if you express the symplectic form, this omega, which at the end of the day turns out to be just a matrix, for the extended phase space, that is, you don't just have position, but you have the four position, you also have time. And not only you have the velocity, but you have the four velocity. So you have what you have in special relativity or general relativity. If you express this in these coordinates, right, then you find this expression where this the metric tensor, the geometry of space-time, comes in as the part that it's in position and velocity, right? This would be position, velocity, position, and velocity. So these diagonal here are the part of the geometry that has to do between essentially counts the state between position and velocity. So one way that you can actually think about the metric tensor as essentially defining the count of states in terms of position and velocity. So the geometry of space-time is intimately related to the geometry of states in terms of position and velocity, which again binds all of this together in ways that I still don't know how it works. It probably needs more research to really flesh out, but that's how it works. And the other very interesting part, which again I have no idea exactly how it works, but this F alpha beta, well, this is the electromagnetic field tensor. This is your electric field and magnetic field appear here as something that counts states in a configuration of position and time versus position and time, which again I can't visualize the geometry of that, but the math tells you that there is a connection to the geometry, and I still don't know what it is. And then you also have this other part, which I think is kind of the inertial part that gives you this count of states. And this is not really a tensor, this is a pseudo-tensor, because this expression does not transform covariantly, I would expect. But again, there is another part here that would be interesting. This would be part of active research of things that I still don't know how to do. And of course one could say, okay, how do you extend this to field theory? And again, I have no idea as well. And this is why it's still research. I don't have all the answer, and I don't think anybody else has. So again, these insights are the result of our research program in the assumptions of physics, and particularly in our approach to reverse physics. If you are interested more in knowing about these topics, I'll put some links in the description. We also have a another channel where we actually do more active research. So if you are interested in contributing something or interested in knowing a little bit about the counteraction, you can subscribe there. And that's all for now, and see you next time.